Section 1, Gravity's Ultimate Triumph, an introduction to black holes. Black holes stand as some of the most fascinating objects in the cosmos. They are regions of space-time where gravity reigns supreme, so strong that nothing, not even light, can escape their grasp. These celestial objects are born from the death throes of massive stars, collapsing under their own gravity. This collapse creates a region of infinite density called a singularity, a point where the laws of physics as we know them break down. Encasing the singularity is the event horizon, a boundary in space-time beyond which escape from the black hole's gravitational pull is impossible. The event horizon is not a physical barrier, rather it is a point of no return. Once an object crosses this threshold, it is destined to fall into the singularity, forever trapped within the black hole's grasp. Understanding the event horizon is crucial to comprehending the bizarre and counterintuitive effects that occur near black holes. Section 2. The point of no return, approaching the event horizon. Imagine a spacecraft bravely venturing towards a black hole, its crew eager to unlock the secrets hidden within. As they approach the event horizon, something peculiar happens. From the perspective of distant observers, the spacecraft appears to slow down, its motion becoming increasingly sluggish as it draws nearer to the point of no return. This apparent slowing down is not due to any mechanical failure or loss of power. Instead, it is a consequence of the extreme warping of space-time caused by the black hole's immense gravity. Time itself flows differently in the vicinity of a black hole relative to observers in weaker gravitational fields. Einstein's theory of relativity revolutionized our view of time, demonstrating that it is not a universal constant, but rather a flexible and dynamic aspect of the cosmos. Time, according to Einstein, is woven together with space to form a four-dimensional fabric called spacetime. Just as a bowling ball placed on a trampoline stretches and distorts the fabric, massive objects like black holes warp the fabric of spacetime. Section 3. A cosmic time warp, gravitational time dilation at the event horizon. This phenomenon, known as gravitational time dilation, is key to understanding the strange behavior of objects approaching a black hole's event horizon. As the spacecraft nears the event horizon, it encounters an increasingly strong gravitational pull. This intense gravity warps spacetime to such an extent that time itself slows down dramatically for the spacecraft relative to observers far away. Imagine a clock on board the spacecraft and another identical clock on Earth. As the spacecraft approaches the event horizon, the clock on board would appear to tick slower and slower from the perspective of an observer on Earth. In fact, as the spacecraft reaches the event horizon, time would appear to stop altogether for the spacecraft relative to the observer on Earth. This doesn't mean that time actually stops for the spacecraft or its crew. From their perspective, time would continue to flow normally. They would experience no strange sensations or distortions of time. Section 4. Frozen in time. The appearance of objects at the event horizon. The immense gravity of a black hole warps time to such an extent that objects approaching the event horizon appear to freeze in time from the perspective of external observers. This freezing in time is not just a visual illusion. It is a fundamental consequence of the warping of space-time described by general relativity. As the spacecraft approaches the event horizon, the light it emits takes longer and longer to reach the distant observer due to the increasing curvature of space-time. This stretching of light waves causes the spacecraft to appear red-shifted, its light shifting towards the red end of the electromagnetic spectrum. At the event horizon itself, the light from the spacecraft is infinitely red-shifted, meaning its wavelength becomes infinitely long and its frequency becomes zero. The spacecraft effectively disappears from view, frozen in time at the edge of the black hole. While the spacecraft may vanish from sight, it has simply crossed the event horizon and entered a realm where the familiar laws of physics no longer apply. Section 5. Einstein's masterpiece, the general theory of relativity. To fully grasp the mind-boggling concepts surrounding black holes and their event horizons, we must delve into the groundbreaking work of Albert Einstein and his revolutionary theory of gravity, the general theory of relativity. Published in 1915, Einstein's masterpiece forever changed our understanding of gravity, space, and time. Prior to Einstein, gravity was understood through the lens of Isaac Newton's law of universal gravitation, which described gravity as a force acting instantaneously across vast distances. While Newton's theory accurately predicted the motion of planets and other celestial objects, it failed to explain certain subtle gravitational phenomena, such as the precession of Mercury's orbit. Einstein's genius lay in recognizing that gravity is not a force in the traditional sense, but rather a manifestation of the curvature of space-time. Imagine space-time as a vast four-dimensional fabric upon which all objects reside. Massive objects like stars and planets create a dent or curvature in this fabric, much like a bowling ball placed on a trampoline. Section 6. Gravity's influence on time, time as the fourth dimension. One of the most profound implications of general relativity is the concept of time as the fourth dimension, intricately interwoven with the three spatial dimensions to form the fabric of space-time. Einstein's theory revealed that just as massive objects warp the spatial dimensions, they also influence the passage of time. This warping of time is known as gravitational time dilation, a phenomenon where time flows slower in stronger gravitational fields relative to weaker ones. Imagine two identical clocks, one placed on the surface of Earth and the other aboard a spaceship orbiting high above. General relativity predicts that the clock on Earth, experiencing a stronger gravitational pull, will tick slightly slower than the clock aboard the spaceship, which is farther away from Earth's gravitational influence. Section 7. Warped space-time understanding gravity's effects. General relativity provides a framework for understanding how gravity affects not only the motion of objects, but also the very fabric of space-time. The theory predicts that massive objects, due to their immense gravitational pull, can warp and distort space-time in fascinating ways. One such distortion is the bending of light as it passes by a massive object. This phenomenon, known as gravitational lensing, occurs because light, despite having no mass, follows the curvature of space-time caused by the presence of massive objects. Gravitational lensing serves as a powerful tool for astronomers, allowing them to study distant objects that would otherwise be too faint to observe. Section 8. Black holes, a testing ground for general relativity. Black holes, with their extreme gravitational fields and bizarre effects on space-time, serve as the ultimate testing ground for Einstein's theory of general relativity. These cosmic behemoths push general relativity to its limits, providing insights into the nature of gravity and the fundamental structure of the universe. One of the most intriguing aspects of black holes is the existence of the event horizon, a boundary in space-time beyond which nothing, not even light, can escape the black hole's gravitational pull. The event horizon marks the point of no return, where the curvature of space-time becomes so extreme that all paths lead inexorably towards the singularity at the black hole's center. The study of black holes and their event horizons provides valuable insights into the behavior of matter and energy under extreme gravitational conditions. Section 9. The unknown depths, unraveling the mysteries beyond the event horizon. While general relativity provides a robust framework for understanding the properties of black holes, it falls short of explaining what transpires within the enigmatic realm beyond the event horizon. The singularity at the heart of a black hole represents a point where our current understanding of physics breaks down, a region where gravity becomes infinitely strong and space-time becomes infinitely curved. According to general relativity, the singularity is a point of infinite density and zero volume, a concept that challenges our intuitive understanding of the universe. At the singularity, all known laws of physics cease to operate, and a complete theory of quantum gravity is needed to describe the extreme conditions that prevail. The quest to understand the singularity and the nature of space-time within the event horizon remains one of the most profound challenges in theoretical physics. Section 10. The quest for a unified theory. Black holes and the future of physics. Black holes stand as tantalizing enigmas at the forefront of modern physics, beckoning us to unravel the mysteries hidden within their depths. These cosmic behemoths hold the key to understanding the fundamental nature of gravity, space-time, and the very fabric of reality. The ongoing quest to reconcile general relativity, which governs the macroscopic world of stars and galaxies, with quantum mechanics, which describes the subatomic realm of particles and forces, represents one of the greatest challenges in theoretical physics. Black holes, with their extreme gravitational fields and enigmatic singularities, serve as a crucial testing ground for any unified theory that aims to bridge this divide. The study of black holes promises to push the boundaries of human knowledge, leading us closer to a complete and elegant theory of the cosmos.